Okay, so in this video we're going to look at the geometric representation of vector addition and subtraction. Now, we've already looked at the geometric representation of vectors, vectors being represented as arrows on a coordinate system, just like this one. And we've also looked at addition and subtraction of vectors outside of the geometric representation. And now we're going to bring those two concepts together. So let's use the diagram here to recap what we know already. So I would like to use this to show the geometric representation of the calculation vector AB plus vector BC. So if we wanted to do this numerically, what we would need to do is we would first need to find the vector from A to B, and then we'd need to find the vector from B to C. So let's do AB in blue. So the vector from A to B is equal to B minus A. So the coordinates of point B minus the coordinates of point A. So the coordinates of point B are 1 minus 1. And I can write them as a column if I want to. And the coordinates of point A are minus 2 minus 2. So to find the vector from A to B, I just need to calculate 1 minus negative 2, which I get 3, and negative 1 take negative 2, which gives me plus 1. So this vector here from A to B it's the instructions of how to get from A to B. So this is what we could have expected from our work last week on the geometric representation of vectors. To get from A to B, we go 3 across and 1 up. And like I said before, we can represent this with an arrow. Hopefully my arrow heads the right way around. I think it is. And let's make the thickness of the line a little bit bigger. There. So that's the vector AB. And we can figure out the vector BC in a similar way. And I'd encourage you to do that as an exercise, and I'll just show you down here. So the vector from B to C is equal to C minus B, the coordinates of C minus the coordinates of B. Coordinates of C are 0, 3. Coordinates of B are 1, negative 1. So minus 1, negative 1. And we get here 0 take 1, negative 1, 3 plus 1 would be 4. And let's just check that. Negative 1 in the x direction, 4 in the y direction, gets us from B to C. So, oh, that's an extremely thick line. Let's make that a little bit thinner. There we go. And that's our vector from B to C. Now, calculating AB plus BC, then in this example, will give us a new vector. So, AB we can put in the 3, 1 that we had from here, and for BC we can put in the negative 1, 4, which gives us 3 take 1, which is 2, and 1 plus 4, which is 5. So we get the vector 2, 5. Now if you notice, if we go from A, if we start from A, which is the first point that we have in this equation, and we follow this vector 1, 2, 1, 2, 3, 4, 5 in the y direction, we end up at C. And actually, that is always what happens. So if we add the vector AB to the vector BC, we get the vector AC. And this is actually the vector AC. So we go from here to here. And we'd like that to be red, please. Okay, and maybe just a little bit thinner so it's a bit clearer. What's going on? So, we've taken AB and BC and added them together, and we get the vector AC. And I can show you that this works all the time. If we have, let's have black rather than red so that we're doing something different, AB plus BC. Now we know that AB, the vector from A to B, can be written as the coordinates of B minus the coordinates of A. The vector BC can be written as the coordinates of C minus the coordinates of B. If we take our brackets away here, we get B minus A plus C minus B. So here we have B, take away B, which of course gives us 0. And we get minus A plus C. And I can just change the order of those and write C minus A, which of course is the equation for figuring out the vector from A to C. So this always works. AB plus BC is equal to AC. And this works as well for any number of vectors that you add together. If you had, for example, AB plus BC plus CD plus DE, then that would give you the vector from A to E. So you can stack them as much as you like, as long as these 2 points match each time, and it'll always take you from the start A to the end E. Now in terms of the geometric representation, the way that this vector here, these vectors here have been represented, is actually the way that we represent vector addition. And I found this a little strange when I first learnt it, I have to say, because actually what this diagram says is if we go from here to here, it's exactly the same as going from here to there directly, which anyone who's walked through a town or used a map would know that going out of your way via point B first to then get to C is of course much longer and less direct, and it's not the same at all as going directly from A to C. However, in terms of the vector representation of addition, they are seen as the same because all we're interested in is the direction that you go in to get from your start point to your end point. And this fact, that it doesn't matter which way round you go as long as your end point is okay, can lead us to another result. So if we have a look here at this set of axes, we have two vectors, A and B. Now I can represent, geometrically speaking, the calculation vector A plus vector B with a third arrow, just as we did in the last example. So the vector A plus vector B is the same as A plus B, which can be represented by this arrow here, as shown. So it doesn't matter if I go that way or that way, I still get to the same point. So this is A plus B. Now, because it doesn't matter which way round I go, it doesn't matter whether I start with vector A or I start with vector B. And you can see, if I copy and paste those. Hang on. Okay, it won't let me copy and paste the vectors. However, I can show you in a different way. This result here would be the same as if I started with vector b from this point. So vector b goes along 1 and up 4. So vector b here would go along 1 and up 4, yeah, just to make sure I get that right. So going from there to there, with vector b first, make that a little bit thinner. So if I first have vector b, and then I add vector a onto this. So vector a is 3 along and 2 up. 1, 2, 3 along and 2 up. You'll notice, here's vector a. Let's put it in red to stay consistent. That I get to the same point. So we can show here that in terms of vectors, vector a plus vector b is equal to vector b plus vector a, because we end up at the same end point. And this is a rule we've looked at before. It doesn't matter in which way you add vectors, it doesn't affect the end result. And in the same way, it doesn't affect the end result geometrically either, because the instructions of a to b, a plus b, are the same as the instructions of b plus a. This is known as the parallelogram rule. Because if you tilt your head slightly, you can see that this is a parallelogram with sides a and b. And we can use this rule to do calculations related to parallelograms. If we had, for example, this is from exercise 12:15 in your book, but you don't need the book to do the exercise. The exercise says we have a parallelogram, A, B, C, D, and we know 3 of the corners, the coordinates at 3 of the corners. So we know, for example, in A, that A is -1, 1. We know that B is 3, 0. And we know that D is equal to 0, 4. Now with all geometric exercises, I recommend the first step you do is drawing a sketch. So we have point A, B, C, D. And we need to figure out what point C is here. So from the exercise, we can figure out the vector from A to B. We could figure out the vector from A to D if we wanted to as well. We could also figure out the vector from D to B, or in the other direction. However, I'm going to suggest what we do is, because we know these two sides are parallel, I'm going to suggest that the best way to find C would be to take the coordinates of point D and add them to the vector A to B. Because if we start at D, and then we go along here, which is the same magnitude and direction as this vector here, so this vector along here is going to be the same, then we'll come to point C. So C is going to be 0, 4, plus A to B are the coordinates B minus A, so 3, 0, minus 1, 1, which gives us 0, 4, plus 4 minus 1, which is 4, 3. So the coordinates of C are the point 4, 3. Now I recommend you do as it says in the book now, and that you sketch yourself a little coordinate system, pop these points in, and check that C is actually where it should be.